Moving on. Lest you think Ohm's Law is limited in application to the simplest of circuits, let me remind you that Ohm's Law is the most fundamental of all electrical properties and can be applied in many, many circumstances, including series circuits, parallel circuits, and more complex series parallel circuits. Given Ohm's Law has a relationship of three properties, current, voltage, and resistance, we can apply Ohm's Law anywhere we know two properties and wish to solve for the third. As a preview of Ohm's Law applications for more complicated circuits, consider the series parallel circuit consisting of three resistors, R1, R2, and R3, arranged in the following fashion. Voltage source E, having a value of 24 volts, is between nodes A and C. Resistor R1, having a value of 40 ohms, is between node A and B. Resistor R2, having a value of 100 ohms, is between node B and C. And finally, resistor R3, having a value of 400 ohms, is also between node B and C. Let's say the only additional piece of data we have about this circuit is a single voltage reading, VBC, known to be 16 volts. Given both resistor 2 and resistor 3 are between node B and C, we now know that both voltage across resistor 2, V2, and the voltage across resistor 3, V3, to also be 16 volts. Let's apply Ohm's Law to see if we can solve for other unknown circuit properties. Consider resistor R2 from node B to C. We know resistance and we know voltage. Current is equal to voltage over resistance. An application of Ohm's Law demonstrates current through resistor 2, I2, is 160 milliamperes. Consider resistor 3, also from node B to C. We know resistance and we know voltage. Current is equal to voltage over resistance. An application of Ohm's Law demonstrates current through resistor 3 is 40 milliamperes. You'll note the parallel elements, resistor R2 and R3, experience the same voltage differential. However, more current travels through the lower resistance path offered by R2, and less current travels through the higher resistance path offered by R3. It makes sense. Same voltage, less resistance yields more current. Conversely, same voltage, more resistance yields less current. Take a look at what's happening at node B. 160 milliamperes of current leaves node B and travels to C through resistor R2. Similarly, 40 milliamperes of current leaves node B and travels to node C through resistor R3. It stands to conjecture 160 milliamperes plus 40 milliamperes, or 200 milliamperes, must therefore be entering node B through resistor R1. This is a preview of Kirchhoff's current law, which states the summation of currents entering a node equals the summation of currents leaving a node. We'll examine Kirchhoff's current law in greater detail in later lectures on fundamental parallel circuit properties. In short, what goes in must come out. Through this application of Kirchhoff's current law, we now have an additional data point concerning resistor R1. We now know the current through resistor R1, I1, must be 200 milliamperes. We know current and we know resistance. Voltage is equal to current times resistance. An application of Ohm's Law demonstrates voltage across resistor R1, V1, or for that matter VAB, to be equal to 8 volts. You'll note the summation of VAB plus VBC, 8 plus 16, equals 24 volts, or the voltage from A with respect to C. This is a preview of Kirchhoff's voltage law, which states that for any closed loop, the summation of voltage rises equals the summation of voltage drops. We'll examine Kirchhoff's voltage law in greater detail in later lectures on fundamental series circuit properties. In short, what goes up must come down. Although I did employ more advanced applications of Kirchhoff's current law and Kirchhoff's voltage law, topics we'll examine in later lectures, you'll note that each application of Ohm's Law, the topic of this particular lecture, for each of the three resistors, can be considered an isolated event. We're given two known properties. Ohm's Law can be used to solve for the unknown third property. As we introduce progressively more and more challenging circuit analysis scenarios, you'll find yourself continuously employing Ohm's Law and will be glad for all the practice you did today. Alright, before we bring this lecture to a close, let's talk about using Ohm's Law to troubleshoot electrical systems. Troubleshooting is the systematic identification of a problem exhibited by a system and the subsequent correction. This is $1 million buzzword for aspiring technicians. Everybody wants to be a troubleshooter. There exists a population of hucksters out there that try to sell troubleshooting as a separate skill, only tangentially related to basic electrical properties, but they are all charlatans, frauds, and swindlers. Anything packaged and sold as troubleshooting without incorporating a thorough understanding of basic electrical properties is mere button pushing, totally inapplicable to real-world problems where what can go wrong often does. If you're enrolled in a hardware lab that accompanies a basic electronics course, you are troubleshooting, even if it doesn't say Troubleshooting Lab in the course description. I know it's frustrating when your instructor says, build me this, show me that, and walks away, and it takes you 2 or 3 or even 4 attempts to get it right. But guess what? All the time you spend finding and fixing mistakes isn't wasted. It's being spent developing troubleshooting skills. That's the point of a hardware lab. Get inside one and make mistakes in a safe and supportive learning environment. Make as many mistakes as you can and make them early and make them often. Make all the mistakes. Get all of the mistakes out of the way up front. Here's the tricky part though. Be sufficiently aware enough to prevent their reoccurrence. Recognize the clues that led you to discovering the mistakes, learn from your mistakes, and never repeat them. Troubleshooting is not a skill separate from basic electrical knowledge. At its most essential level, troubleshooting is the systematic application of basic electrical properties. Think of the term law. Ordinarily, we think of laws as things you get sent to jail for or pay a fine if you violate them. Ohm's Law is not that type of law. There's no Ohm's Law jail if you violate it, and you can't pay some lawyer to twist the wording of Ohm's Law to make your circuit work like you want to. Ohm's Law is a law like gravity, and that it goes to work every second of every day and cannot be violated. Reality always obeys Ohm's Law, and it's your job as a troubleshooter to interpret reality. Say, for example, you're tasked with troubleshooting a system that habitually trips an overcurrent protection device, or, lacking overcurrent protection, has an annoying tendency to burst into flames. Fire is a pretty good indication that the ampacity or current carrying capability of this device has been exceeded. Even if you have never seen the system before, nor even have the remotest idea of what it does, as an effective troubleshooter understanding Ohm's Law, you are aware of 2 possible causes for this problem. If the current is too high, either the voltage is too high, or the resistance is too low, or maybe both. There are simply no other possible explanations for this occurrence. You don't need a $50 flowchart to tell you this, and it's not like Ohm's Law is some magic secret. At its heart, your understanding of Ohm's Law quickly and efficiently cuts out a whole lot of dead ends and useless busywork. Determining why the voltage is too high, why the resistance is too low, or both is the next step in troubleshooting. This is where an intimate understanding of how a system is intended to operate comes into play. It is my intention not to roll out a flowchart that shows you how to troubleshoot a single system, but rather arm you with sufficient technical knowledge to understand and thus troubleshoot any system. This is not some paint-by-numbers, quick and easy scheme where you can send some dude in the back of a comic book $50 and they'll send you a black belt in Kung Fu. I'm going to tell you right now, this is going to be a long, hard, and grueling road full of bruises, sore backs, hurt feelings, and crushed expectations. You need to have the strength of character to recognize that all this hard work will be worth it in the long run. The point is, a skill like Ohm's Law is a basic principle, equivalent to learning how to throw a decent punch if you're training for a fight, and it needs to be practiced, drilled, and developed over and over until it becomes an automatic response necessitating little cognitive resources. That's the purpose of study. It's hard and exhausting for a reason. You're developing important skills that need to become habits, and the only way to do so is through repetition and practice. Regarding good work practices, you simply must perform the calculations first. That way you know what to expect. Make sure you use the correct components. Make sure you connect them in the correct manner. Make sure you supply them with a proper level of voltage, and make sure you take measurements in the right place. In short, imagine how well lab will go if you know what you're doing. Don't just randomly pull wires, push buttons, and hope it works out okay. In this spirit, here's a couple simple troubleshooting scenarios that will test your basic understanding of Ohm's Law. As basic and contrived as these scenarios might be, don't for a moment underestimate the importance of Ohm's Law. Trust me, you'll find ample opportunities to employ Ohm's Law in more complicated troubleshooting scenarios. Let's say we're tasked with building this simple circuit where a 20-volt source is supplying current to a 1 kilo ohm resistor. Do the calculations first. What's the current you would expect flowing through this circuit? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Current is voltage over resistance. An application of Ohm's Law demonstrates we should anticipate 20 milliamperes of current. Let's say we build this circuit, and as soon as we turn on the power supply, current spikes to 200 milliamperes, and rather quickly, the resistor's paint job turns an ugly shade of brown, starts smoking, and is soon engulfed in flames. What's the problem? The answer is right in front of you if you know where to look. There's really only three elements in this simple circuit: the voltage source, the ammeter, and the resistor, so it's obviously one of these that are at fault. Let's say a quick check of the voltage source with your voltmeter indicates the source really is at 20 volts. What's the problem? It's your lab partner. I warned you about this, didn't I? Instead of grabbing a 1 kilo ohm resistor with a brown, black, red, gold 4-band color code, i.e. 1 0 with 2 zeros, they grabbed one with a brown, black, brown, gold 4-band color code, i.e. 1 0 with 1 0 or 100 ohms. Pay attention to the third band. Didn't I say that before too? Pay attention to your lab partner. Never trust them. A 100 ohm resistor provides substantially less opposition, 900 ohms less to be exact, than the specified 1 kilo ohm resistor. An application of Ohm's Law demonstrates that the smaller 100 ohm resistor with a 20 volt differential across it should experience 200 milliamperes of current, i.e. 10 times greater than what we anticipated. No wonder it burst into flames. Ohm's Law says current will be high for low resistance paths. Tying this troubleshooting example to the development of good lab practices, had you taken the time to measure the resistance with an ohm meter, or at the very least interpreted the 4-band resistor color code prior to turning on the power, this whole sordid tale would never have happened. Your lab partner isn't just there to make you look good. They're there to dummy check your work. And believe me, you are there to double and triple dummy check their dumb work. Here's another very simple troubleshooting example necessitating your understanding of Ohm's Law. Let's again use a 20 volt source and a 1 kilo ohm resistor. This time it really is 1 kilo ohm because no way are you going to fall for that one ever again. Let's say you observe no voltage drop across the 1 kilo ohm resistor, nor do you observe any current. What's the problem? If there is no voltage drop across the resistor, it means there is no current through it. Ohm's Law says so. Voltage equals current times resistance. 0 amps times 1 kilo ohm is 0 volts. First, ask yourself, did you turn the source on? You'd be surprised how many troubleshooting scenarios are resolved simply by pressing the large button that says on. I've done this myself more than I'd like to admit. What if the source was on, and you still observe no voltage drop across the resistor, nor any current through it? Ask yourself, what is stopping current? Perhaps something with an infinite resistance. I previously assured you that it was in fact a 1 kilo ohm resistor. However, are it and the ammeter the only elements in the circuit with this source, or is there something else in series with it? Think about what I'm asking. What is something with an infinite resistance? Something with an infinite resistance is an open or an incomplete circuit. This is where intimate knowledge of your circuit building environment, typically a protoboard in lab, comes into play. You may have the correct voltage, and you may have the correct resistor, but a complete circuit may not exist because of an inadvertent open. A complete circuit, including an ammeter, looks something like this. Current leaves the positive terminal of the voltage source, enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, enters the top of resistor R1, travels through resistor R1, leaves the bottom of resistor R1, and returns to the negative terminal of the voltage source. An open anywhere in this path would prevent completion of the circuit and disrupt all current flow. Consider an open between the voltage source positive terminal and the ammeter indoor. Current won't flow because no circuit exists. Another possibility for an open exists between the ammeter outdoor and the resistor. Current again won't flow because no circuit exists. Another possibility for an open exists between the bottom of the resistor and the negative terminal of the voltage source. Current again won't flow because no circuit exists. Finally, consider the test leads in the ammeter itself. Instruments like ammeters often include internal fuses to protect the device from high currents. In the event of a ruptured fuse, the ammeter itself prevents completion of the circuit and thus no current flows. Additionally, consider the consequence of damaged test leads or test leads that are not properly inserted that prevent completion of the circuit. In summary, if you observe no current flow, you are definitely dealing with an open. Having determined an open as the source of your problems, it's now up to you to find it. Oftentimes, one needn't resort to instrumentation to find the source of the problem. Just look at it. You might find a wire dangling out into empty space, or a component or wire misplaced or landed on the wrong spot. Attention to detail in viewing the circuit from several different angles might reveal the cause for the missed connection. As some general advice to aspiring technicians, I will be so bold to proclaim that fully 99% of all electrical problems you will ever encounter in the field are the result of open circuits. Either some wire wasn't properly tightened on a screw terminal, or it was properly tightened and shook loose, got pulled out, or got cut. Last but not least, do not rule out the possibility of improper use of instrumentation being the source of your problem. This caution is especially relevant when your lab partner is behind the wheel. If one is employing a voltmeter incorrectly, one will not be able to properly measure voltage. Similarly, if one is employing an ammeter incorrectly, one will not be able to properly measure current. We'll examine the proper application of voltmeters and ammeters in later lectures. In closing, realize there is no way one can possibly foresee and anticipate all possible sources of problems within a system, and anyone who says so is a liar. I am not saying that technicians accustomed to troubleshooting by the book or using some company-established procedures cannot resolve errors, but I am saying that a flexible technician with knowledge of basic electrical properties like Ohm's Law can resolve errors that aren't even in the book. Before we wrap up, here's a consolidated list of some of the general troubleshooting advice we discussed today. Again, this advice cannot possibly cover all possible scenarios, but in my opinion, it is sufficiently general enough to encompass some basic principles of troubleshooting for your first couple DC circuit labs. Open circuits mean infinite resistance and result in no current. Short circuits, in contrast, mean low resistance and result in high current. If you can walk away from this lecture understanding just these two simple facts, I will consider my efforts having not gone in vain. If you can't remember both, remember this one. Open circuits do not allow current to flow. If you turned all possible troubleshooting scenarios into animals, where their population is representative of their frequency of occurrence, the open circuit is like a beetle, which even if you combined all other species on Earth, would still outnumber them like 1,000,000 to 1. Your first error is your dubious choice of lab partners. Your next 999 errors are going to be open circuits. Do the calculations first. Know what to expect. Do not bring a dull knife to a gunfight. By doing the calculations up front, you'll have a basis of comparison if your observations match your expectations or if they are wildly wrong. Double check your components. Make sure you're using the right components and install them correctly. Read the values on the side. If you can't read the value, use an ohm meter to measure and verify the specified value. Check to see if a switch works before you put it in a circuit. Resistance of a closed switch should be close to 0 ohms, whereas the resistance of an open switch should be infinite. Test everything because lab equipment gets hammered by generation after generation of students. Sometimes out of sheer exhaustion, components, test leads, or meters just die. Double check the circuit. Make sure it's hooked up as intended. Use colored wires and label the nodes. Look at anything you suspect of being open from all angles, not just the top. Different viewpoints often quickly reveal a missed or off by one connection. Supply your circuit with the correct voltage. Verify output voltage before and after you hook it up to your circuit. Use your DMM to check it. If you're going to use your DMM, use it properly. We already covered the ohm meter in a previous lecture. We'll go into details about voltmeters and ammeters real soon, but recall the basics. Use the checklist. I am not urging you to use this checklist every time. I am demanding you use this checklist every time. The use of this checklist will save your measurement equipment and circuit a lot of costly downtime and may potentially save your life. I am not overstating the benefits of using this checklist. Use the checklist. Think about it. Really think about it. Take your time and think before you act. The checklist has 4 steps. Follow them 1 through 4, and you will get it right every single time. Skip a step, do a step wrong, or do a step out of order, and you will get it wrong every single time. Function. Choose the quantity you want to measure. Voltage, current, or resistance. DMMs use different detection mechanisms to measure different quantities, and if your DMM is in the wrong mode, it won't work. Leads. Put your leads in the correct place. For voltmeter and ohm meter mode, the leads go in one place, and in ammeter mode, they go in a different place. Of note, customarily the red plug goes into a red hole and the black plug goes into a black hole. You would be surprised how many people mess this up under stress. Range. If your DMM is not auto-ranging, one must manually choose an appropriate range to obtain the most accurate measurement results. Whereas if your DMM is auto-ranging, your DMM will automatically pick the most appropriate range to obtain the most accurate measurement results. Related to range, be aware there is a limited range a meter and you can safely measure. Do not exceed this range or you will damage the meter and or yourself in the process of doing so. Certain levels require appropriate levels of PPE or personal protective equipment to measure them safely. Placement. This is the single most important step. One must put the DMM in the correct place to take the measurement of interest. Put it in any other place than the proper place, you won't be able to take the measurement you desire, or you'll damage the meter, your circuit, or yourself. Remember, ohm meters are never used on live circuits. They read the resistance from terminal to terminal with the device of interest removed from the circuit. Voltmeters, in contrast, read voltage across something. Voltage is a 2-point measurement. Finally, ammeters read current through something. Current is a single-point measurement which must flow in an indoor and out an outdoor. Your circuit may be completely functional, but you might be measuring it improperly. Improper use of a DMM might not just result in bad measurements, you might damage the meter, your circuit, or yourself. Finally, if you are absolutely certain your circuit is functional and it's still not conforming to your expectations and calculations, reanalyze your expectations and calculations. That's science, dudes. At any moment, I am prepared to abandon long-held convictions because rigorous and proven observations have demonstrated otherwise. Mankind no longer believes angry gods are the cause of thunder and disease because it's been scientifically proven that thunder and disease are caused by ghosts and aliens. Look it up. This is not to say that your circuit will ever disprove Ohm's Law. I've yet to witness a lab group do this. I have, however, on numerous occasions, observed students using something I call Ohms Law, the opposite of Ohm's Law. If your observations aren't jiving with your numbers and all else has failed, check your numbers. You might be using them wrong. Finally, trust no one. Verify. There will come a time when you are working on circuits and systems that have the potential to injure or kill you. Your life is on the line. Check to make sure all sources of hazardous energy are locked out and tagged out prior to initiating work. Bad habits are hard to break. Start safe work practices now. Okay, that about wraps it up for this introduction to Ohm's Law lecture. Here's one last visual on Ohm's Law that I never grow tired of showing students. I think this should be a mandatory poster in every lab environment. It goes well accompanying a kitten clutching a branch saying, "Hang in there, buddy." In conclusion, this lecture took a close look at the most fundamental of all electrical relationships known as Ohm's Law. We learned the cause, effect, and opposition relationship between voltage, current, and resistance, and used it to calculate unknown quantities given known or observed inputs. Additionally, we had a general introduction on troubleshooting basic electrical circuits using Ohm's Law. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.